All right. Thank you. So just a short outline. I'm going to begin by talking about Weinstein domains. So these will be certain symplectic manifolds that you build by attaching handles along isotropics and Legendrians. And then I'm going to state the H principle for a certain class of Weinstein domains. And so there'll be a certain subclass of Weinstein domains that satisfy an H principle. And then I'll explain how to use that H principle to conclude something about all Weinstein domains. Okay. Arbitrary Weinstein domains. So again, the H principle won't hold for all Weinstein domains, but you'll be able to leverage the H principle to say something about arbitrary ones. Okay. All right, so let me begin by giving an overview of Weinstein domain. So definition, it's a symplectic manifold. First is exact if symplectic form is the exterior derivative of some one form lambda, and then an exact symplectic manifold has. So I should first say that if a symplectic form manifold is exact, then it cannot be closed. It must either have boundary or it must be open, basically by Stokes' theorem. And so let's assume we're in the compact case. So it has boundary, and then we say it has contact boundary if X with this one from over here, or let me just say kernel of lambda restricted to the boundary is a contact manifold. So you require this one form to be nicely behaved near the boundary so that the boundary has this contact structure. And this actually turns out to be equivalent to the existence of a certain vector field. So the exactness is equivalent to, there is a vector field which is called the Liouville vector field, V on X, so that the Lie derivative of the symplectic form in the V direction is the symplectic form. So this exactness condition is equivalent to having a vector field V, that the Lie derivative of the symplectic form is symplectic. And this just means that if you flow in the V direction, then the symplectic form expands. So V is this expanding vector field. And this contact boundary condition is equivalent to the condition that V is transverse to the boundary. So what are examples of such things? Well, a cotangent bundle, symplectic with the standard symplectic form. Right, this actually is exact. And it has primitive given by this one form, which is called the Liouville one form.
Sorry, what is that to the left of T star M?
This is part of the bracket. Sorry. This is example. Okay, and what is V? What is this Liouville vector field in this case? It's just the radial vector field in the P direction. So here we have M. So and this is the cotangent bundle of M, so it's kind of a thickening of M. And this radial vector field is in the covector direction, and it's transverse to well, okay, if you take a compact piece of the cotangent bundle, then it will be okay, if you fix a metric on M and you look at all covectors with length less than 1 or equal to 1, then this vector field will be transverse to that boundary. So in particular, this boundary, which is the unit sphere bundle, has a contact structure. So this is this unit cotangent bundle. Of the contact structure. And this is related to the contact structure that we've been talking about on one-jet spaces. But this is up in a closed manifold. Okay, so that's some background about exact symplectic structures with contact boundary. And now let's define what a one-tree structure is. Definition, an exact symplectic. So I'm going to incorporate V into the definition. Say this is so having the V is equivalent to the choice of V is equivalent to the choice of lambda, if such things exist. And we say that this is Weinstein if this vector field V is nicely behaved. And so what does nicely behaved mean? It means that it's gradient like for a function. But even better, you usually take the function to be Morse. There's a Morse function. So that V is gradient like for P. So in the exact symplectic case, you have this little vector field, but it might be some crazy vector field. It might even have closed orbits. But in the Weinstein case, the vector field is tamed by this Morse function. So in particular, it cannot have any closed orbits. So it's just a much better behaved vector field.
What was the definition of gradient like?
Gradient like. So let's see. I'll probably mess this up. I think maybe this. Someone might have to correct me. Okay, I mean basically, you want that. Okay, is this
You want to write d phi on the right hand side.
d phi? Okay, but with that condition, is it okay more or less? Yeah. Okay, basically, it's a weakening of the condition that V is the gradient of V.
So you no longer require that it's transverse to the boundary.
No, you still require that.
Okay.
This whole okay. With exact symplectic with contact boundary.
Okay, yeah.
And this Morse function, well, okay, you want it to be proper, and then okay, in the compact case, you want its gradient or this vector field V to be transverse. Yeah. I mean, as I think we saw in some of the problem sessions, you can cook up a function on an open manifold without any critical point, but this function is going to be very badly behaved near the boundary, and so that's not really going to tell you anything about the topology of the space. So you have to impose some conditions, and the conditions are that the function kind of looks nicely near the boundary. Maybe it's just projection onto one of the coordinates, or it's proper. So you definitely need some conditions near the boundary. Okay. Okay, so this is what a Weinstein domain is, but this is equivalent. Okay. So the definition I had up there, this is actually equivalent to the following. So in smooth Morse theory, or smooth topology, a Morse function gives us a handle body decomposition for our space. Each critical point gives rise to a handle for the decomposition of the space. And this is a Morse function, so it does give us a handle body decomposition for a space, but it gives us a special type of handle body decomposition. So what does the handle body decomposition for a Weinstein domain look like? Well, there's a index 0 critical points always. So neighborhood of that index 0 critical points is just going to be the standard symplectic ball with the standard outward pointing Liouville vector field. So I'm saying the index 0 one is just this ball. Its contact boundary is just the standard contact structure on a sphere. And then for each other critical point that you have, you attach a handle. So maybe I have an index k critical points. It turns out that passing through this index k critical point is the same thing as attaching a handle. And this thing is called the Weinstein handle because they were first constructed by Weinstein. Now, when we, is there chocolate colors?
Yeah.
Oh, I'm not sure which of these colors look best. So here we have this attaching sphere, and this attaching sphere is actually going to be isotropic. And it's isotropic meaning, remember, this is a contact manifold, and this attaching sphere lies in the contact distribution. And furthermore, after you attach this handle, this is again a Weinstein structure, and so this has a Liouville vector field. The handle has a Liouville vector field. So kind of the handle looks something like Liouville vector field is inward pointing near this attaching region and outward pointing away from the attaching region. And so that's outward pointing in the new boundary that you've created. The new boundary is another contact structure. And you can, again, attach another Weinstein handle along some other isotropic in this new contact manifold and keep going. So the game is, you're at some contact manifold you find a isotropic sphere, which should have a framing, and then you can attach a handle. And the claim is that the symplectic structure extends to create a new symplectic manifold with contact boundary.
I always assume the handles are attached in order of increasing index.
You can always, so I'll talk about handle moves, but a priori, this is not the case. Okay, so some other things that are important in the handles. So there's the attaching sphere, which is isotropic in the contact sense, but then there's the core, which is isotropic in the symplectic sense. So there's this core disk, isotropic core disk, which this is an index k handle. This is dimension k, and this attaching sphere is dimension k minus 1. Now, isotropic in the symplectic sense means that the symplectic form vanishes on the core. Okay, so this is the picture.
Sorry, Oleg, can I ask one more question about this gradient like thing?
Yeah.
If V is actually the gradient of phi, then the left-hand side equals V squared, right? I'm not sure if I understand what this inequality means.
That seems right. Yeah.
So, but then V is not.
You might want a constant there. Or something.
Yeah, you want to allow some constant on the right hand side.
Okay, constant in front of
Everything on the right hand side.
Like parenthesis on right hand side and a constant
Okay.
multiplying it.
Right. Thank you. Okay. So this is the this is the anatomy of a Weinstein handle. Yeah.
Can you give an example of an exact symplectic manifold that is not one state?
Those are pretty hard to produce actually, and I'm not gonna give it any stock. Yeah. And the point is that Weinstein is actually quite easy to produce because it's actually quite easy to come up with isotropics. I mean, we have H principles for them. Yeah. So there's not a lot of supply of things that are exact symplectic that are not Weinstein. I mean, I think there's lots of open questions about that actually.
Sorry. You said the core has to be isotropic. Doesn't this mean that there is a bound on the dimension of this core? Like
Yes,
pretty
that's the
small?
next thing I was gonna say. Yeah.
Okay.
So because the cores are isotropic, remember that the dimension of any isotropic. So let me put it this way. The index of the handles. This is the dimension of the core, and the core is an isotropic. So it has, because the core is isotropic, its dimension is at most n, which is half the dimension of x. So all the handles have index at most half the dimension, and it's also a general theorem that the whenever you have a Morse function, the whole manifold deformation retracts to the union of its cores. So x2n deformation retracts to the union of the cores of all the handles. And the union of the handles is an n-dimensional, more or less, CW complex. So even though X has dimension 2n, its deformation retracts, in particular, has a homotopy type of a half-dimensional CW complex. And this is connected to what I was saying before. An exact simplex manifold always has boundaries. So you can assume it has the homotopy type of a 2n minus 1 CW complex. But if you have this Weinstein condition, it actually deformation retracts something much smaller, which is of half the dimension. So there's some topological conditions on what can be Weinstein. Closed manifolds can be Weinstein. A lot of other manifolds can be Weinstein. Okay. And I
Or did you say that exact symplectic manifold have also a dimension bound, a handle dimension bound that is?
I just said that they have to have boundaries. So
yeah,
their dimension is 2n, but they must deformation retract something of 2n minus 1. Because,
okay.
So, but there are, so I guess maybe just a remark. Someone asked about exact symplectic things which are not Weinstein. Example, there are exact symplectic four manifolds with like third homology not 0. Versus the Weinstein thing would have to have third homology be 0 because it has the homotopy type of something half the dimension. So all the homology above 2 would be 0. So this example, which I think was originally constructed by McDuff, is exact symplectic, but not Weinstein. But it's a bit complicated to construct right now. Okay. And
are there examples with the right homology which are you read but not Weinstein?
no, I mean we don't know.
You will.
Yeah. So I'm going to focus mostly on Weinstein things, or completely on Weinstein things in this talk because they're easier to construct. Our H principle tools apply. Also the computational tools when we apply in that setting. So, okay, another thing that's worth mentioning is that these cores, remember, are isotropic. So you should think of so X deformation retracts to the union of cores, which is a singular isotropic. So you should think of X, okay, as roughly being cotangent bundle of its cores, which is going to be a singular. It's going to be an isotropic in here, so I'll say singular isotropic, right? Just like cotangent it's cotangent of a smooth submanifold. A general Weinstein domain should be thought of as a cotangent of the singular isotropic. In this case, where I just have two handles, this is one of the cores and this is the other core. So the union of the cores is this plus this, which is singular, but it's isotropic in each disk. So that's another way of thinking about Weinstein domain. Okay. Maybe one final thing to say is that there are natural examples of these things. So other examples are dynamomes, which are manifolds or complex manifolds with proper holomorphic embedding into Cn. So affine varieties, for example, those are examples of Weinstein domains. And actually, it turns out that any Weinstein structure can be deformed to a Stein structure. The Weinstein structure, it has just a symplectic form plus this Morse function. Turns out any symplectic manifold has a almost complex structure, but there's an H principle that actually lets you upgrade that almost complex structure to an integral complex structure. And furthermore, your Weinstein Morse function helps you create this proper holomorphic embedding into Cn. So sometimes these are actually equivalent viewpoints. But you have to consider complex Stein domains up to deformation. So you actually are deforming the complex structure, which is something that most people in complex analysis don't really do. But if you allow that, then the theories become more or less equivalent. Okay.
The claim was your Weinstein can only if you can be built in this way.
Or alternatively, you have this Liouville vector field that's tamed by a Morse function. But these are equivalence formulations.
If the core is smooth, is it true that X is a cotangent bundle of the core?
JD says yes. And maybe you prove this. I think that's in your book, actually. Yeah. But that's in the new book? No, from Stein to 1, Stein and back. Oh, really? Yeah. Okay. All right. So there's experts here. Let's refer to the experts.
Well, if the core is half dimensional, it could be less than half dimensional.
Right.
Then it's not a potential.
Right.
It's half dimensional.
No, but even in okay, well, yeah.
Well, a neighborhood, maybe for tangent bundling, everything will track on usually.
Okay. Yes. Okay. All right. So now let's talk about H principle. So what's the formal data here? So definition. A formal symplectic structure. X is it's non-degenerate. Remember, a symplectic structure is a closed non-degenerate two form, and the closedness condition is some PDE. The non-degeneracy condition is just some pointwise tangential condition, and that's all you remember. So you forget the closedness. This formal symplectic structure. This is also equivalent to having an almost complex structure, which is also a pointwise condition. Okay. Now I'm going to introduce some special classes of Weinstein domains. So we say that a Weinstein X. So I'm going to drop all this notation that I've introduced before. I'm going to drop the symplectic form. I'm going to drop the Morse function. But when I write X, you should really remember that there is an explicit handle body decomposition that I'm talking about. So Weinstein X is subcritical if all Weinstein handles an index strictly less than n. Okay. And why this definition? Well, in that case, the attaching spheres are subcritical isotropics. And we've proved some special things about subcritical isotropics, namely that they satisfy an H principle. Okay, well, remember, Weinstein domain, all the handles have index less than or equal to n. Now, let's consider a certain class of things that do have index n handles. So let's let n be at least 2. We say that X is flexible if all index n handles are attached along loose Lazarevians. So remember, yesterday I said that a loose Legendre is a Legendre that has this loose chart, kind of a zigzag across a wide enough interval in it. And these also satisfy an H principle. Okay, but in particular, if you are flexible, if you are subcritical Weinstein domain, you are flexible because you don't even have any handles of index n. But both of these definitions depend on a particular presentation of your Weinstein domain. Now let me draw some pictures. Let's say the simplest non-trivial Weinstein domain is a cotangent bundle of a sphere. The sphere has a Morse function with 2 critical points of index 0 and index n. You can kind of apply the cotangent bundle operation to the whole picture. You would get a Weinstein structure here with an index 0 and an index n. So that presentation means you start with the standard symplectic ball, and then you attach a single index n handle. Well, that's attached along some Legendrian sphere. Which Legendrian sphere is it? Well, it actually turns out to be this flying saucer Legendrian, which is called the Legendrian unnut. So here we're depicting this in I guess the front projection, but it's really living in R2n-1, which is living in the standard structure in a sphere. This is what's called the Legendrian unnut. Okay. So there's an index 0 here, and inside this handle there's an index n. Okay. And so what I'm saying is there's an operation that takes you from Morse functions on smooth manifolds to Weinstein Morse functions, the Weinstein manifold, namely by applying the cotangent bundle. Yeah.
Can one say, for instance, that in this example, there is no presentation which is flexible? So if you just fix the symplectic structure, but not the.
Yeah, that's a claim. Let me give an example in a second.
Okay.
Yeah, the next thing I was going to say is that there's the flexible version of this. I would call this the flexibilization of this one. And what you do is you just have the same picture, you look at the index n handles, and you just add a zigzag to that Legendre. Let me make this a little bigger. So I just formally insert a zigzag. And in high dimensions, if n is at least 2, remember I said you can add these zigzags in a way that doesn't change the formal class. In dimension n equals 1, adding a zigzag always changes the formal class. So for n equals 1, these two will not even be formally the same. But if for n greater than 1, the cotangent bundle is, this cotangent bundle is formally symplectomorphic to this flexibilized cotangent bundle, which so these are diffeomorphic, and formally symplectomorphic means that the symplectic forms here are homotopic through non-degenerate two forms. And that's just because these Legendrians, if I'm careful enough, are formally isotopic through Legendrian embeddings. Again, you have to be a little careful. You have to pick a U with Euler characteristic 0, attach the zigzag along that, but then the formal classes are the same. This is quite easy to prove, but the harder statement is that these are actually not, these are not symplectomorphic. So they're formally symplectomorphic, but they're not genuinely symplectomorphic. And this is a manifestation of symplectic rigidity. And again, you need some non-classical invariants here. So this uses things like J-homomorphic curves, Floor theory, etc. So, like, classical algebraic topology is not going to be able to detect the difference between these. Okay. So in particular, a full H principle does not hold. At least this already shows that you have non-injectivity on pi 0. Right. But we know that there is an H principle for isotropics that are subcritical or loose Legendrians. That's what we talked about last time. And the H principles for those attaching spheres should give rise to H principles if you restrict to the class of Weinstein domains which are subcritical or flexible. So this is an H principle of Chilibach. Yasha, Rashford. So I guess I should say that there's a further formal condition to be Weinstein. It's not just having this almost it's not just having this non-degenerate two form. We've already seen there's a topological condition, namely that all the handles have to have index n. And you have to have, which is equivalent to being the homotopy type of a half-dimensional CW complex. So let's suppose X2n has the homotopy type of an n-dimensional CW complex. Let's let n be at least oh, sorry. Oh, I'm sorry. This should be 3. Should be n at least 3 because you're attaching along n minus one dimensional Legendrians, you want the Legendrian to be at least two-dimensional, right? Because if n is two, the Legendrian is one-dimensional, and stabilizing changes the form of variance. So actually n has to be at least three. So that. Okay, then they proved at least a pi zero H principle. I don't know about the status of a full H principle, so I'm just going to state that. Then pi zero, Weinstein structures are subcritical. Pi zero of this I'll say symplectic structures that are formal. So this non-degenerate form, this is an equivalence. Oh, maybe this is yeah, this I guess requires that X has the homotopy type of something that's less than n. And then okay, sorry, let me back up. The one that's subcritical is true even for n equals 2. And then furthermore, if n is at least 3, then if you restrict to flexible Weinstein domains, so those are things that these attachment features are these loose Legendrians, then there's an H principle as well.
Isn't there like some subtlety that you actually need a Morse function with critical points
Yeah,
below the
I mean,
index?
that's the actual condition. We need a Morse function with only critical points up to index n.
Right. Okay. Yeah. So maybe I should have
Sure,
said
type.
over here that we are really okay. When X has the homotopy, yeah, I guess this you're saying that this thing over here should also.
No, I'm just saying instead of homotopy type.
But I think in if n is at least.
I mean,
Are these not equivalents? At least in high dimensions, I think it should be.
if dimensions at least 6 is probably okay, yeah.
Yeah.
If you're in dimension 4, I'm not so sure.
Okay, yeah, that's okay. So maybe this should be slightly improved. Should have a Morse function, but just a smooth Morse function
Yeah.
with index less than n.
So what is pi
Or
zero?
less than equal to.
What is pi zero of Weinstein?
So I'm gonna say something about that in a second. Yeah, so yeah, you have to make sense of paths of Weinstein structures, so you have to talk about some way of modifying what are Weinstein structures. I'm gonna get to that in a second. But I just wanted to write down this version of the H principle first. But the takeaway is that if you restrict to the subcritical or flexible Weinstein structures, then you have an H principle. But for general things, you don't have an H principle. Like the standard cotangent bundle is not symplectomorphic to the flexible one, even though they're formally the same. And actually, there's infinitely many Weinstein structures on a cotangent bundle, which are not symplectomorphic, even though they are formally symplectomorphic. So it's very far from being injective. Like the kernel is of the forgetful map from all Weinstein structures to formal symplectic structures is infinite.
So when you say there that T star send is not symplectomorphic to T star send flex,
Yeah.
that's not for symplectic manifolds, it's to Weinstein manifolds.
These are not the same. Okay, so I'll say, okay, well, first of all, these just have different Weinstein structures, but maybe there's some moves, as I'll say in a second, that take this one to this one. Turns out this is not the case, but even more so, they are not symplectomorphic.
Okay, not okay.
Okay, so they're not symplectomorphic. They're not equivalent in any kind of Weinstein sense either. Yeah, they're in different components of pi zero of y. Yeah.
There's no claim about the non-emptiness of these spaces, right? Like,
Claim about what?
like it's not clear to me if you just assume that it has a homotopy type of. Are you claiming that there exists a Weinstein structure and that this inclusion is a homotopy equivalence, or it can be empty? The space of Weinstein structures can be.
Okay, the claim is if X has a Morse function with indices less than n or equal to n, and it has a all formal symplectic structure, then in high dimensions, it will actually have a Weinstein structure, which turns out to be flexible. So that's surjectivity of this map. And furthermore, if you have two flexible Weinstein structures, then they're connected through some Weinstein moves that I'll say something in a second, which actually implies that they are symplectomorphic.
And but the space of formal symplectic forms can be empty.
It could be empty, yeah.
In the subcritical case, just subcritical, there is not, you did not know what happened with phi one.
Yeah, I don't know. I haven't thought about higher homotopic groups in this sense.
Homotopic type less than n was part of the conclusion for the first case.
Sorry, can you say that again?
I'm sorry, when you wrote homotopic type less than n, was that part of the conclusion of? That wasn't.
No, that was kind of like this case. This like to even have a subcritical Weinstein structure, you should have a homotopy type something less than n, strictly less than n, and you should have a Morse function with critical points strictly less than n. But then you can cook up a Weinstein structure on it, which will be subcritical, even for n equals 1. So if you have a smooth manifold with just index 4-dimensional smooth manifold with just index 0 and 1s and a non-degenerate 2 form, then it has a Weinstein structure, even for like this n equals 2 case. Basically because of this like formal class issue that occurs in n equals 2, which corresponds to 1-dimensional Legendrians. Not everything like this. The map from Wine to Sim is not even surjective for n equals 2. Okay, so let me talk about what I mean by pi 0, and so I have to say what I mean by paths between Weinstein structures. So I need to introduce some moves. These are Weinstein handle moves, or this is also called the Weinstein homotopy. And so what are these moves? Well, first, you can isotope attaching spheres through isotropics. You can cancel or create handles, but you can only cancel them if they are in canceling position. And these handles have consecutive indices, so what does this picture look like? Suppose you have an index n-1 handle, and then you have an index n handle whose attaching sphere goes through the n-1 handle exactly one time. Then you can cancel to get rid of both of these handles, but conversely, you can create two canceling handles out of no handles. So that's another move. And then you can exchange order if this attaching sphere is disjoint from what's called the belt sphere of the other handle. So the picture is something like this. You have a handle like this, you have a handle like this, and in this picture you attach this one first and then this one, but this attaching sphere is disjoint from this sphere over here, which is called the belt sphere. Then you can push this one down and push this one up, so you would get a picture like this, where this one is actually attached first and then this one is attached. So these are the same moves that you see in classical Morse theory. And the point of these moves is that they don't change the symplectomorphism type. So this is kind of the key. These moves don't. These moves preserve the exact symplectomorphism type. So going back over here, I said that these two are not symplectomorphic, and in particular, there's no Weinstein homotopy moves. Let's start with this presentation and go to this presentation. Because if there were, then by this remark over here, they would be symplectomorphic. So having a Weinstein homotopy is strictly stronger, or we don't know if it's strictly strong, but it's at least as strong as having the same symplectomorphism type. Okay. Okay. And you can actually combine some of these moves to get another move, which is the handle slide. The handle slide is actually going to be just a combination of this exchange move and this isotopy move. So a handle slide, you have two handles of the same index. Okay. And then you start sliding this one over this one. So what that means is maybe they're both attached at the same time originally, but then you push this one down a little bit and push this one up. So now this one is on top. The attaching sphere of this one starts sliding over. So now it kind of looks like it's engulfing this other handle. And then you keep pushing. You push this attaching sphere past the belt sphere of this one until this one actually comes back down to the same level set. And so they are, at the end of the day, attached at the same time, but the attaching spheres have changed. So here, these were maybe the original attaching spheres, but the attaching spheres over here, one of them stays the same, and one of them becomes the connect sum of the original two. This is the schematic picture. I should say, like later on in the talk, it's going to be important to actually have an explicit model for what this handle slide does to the fronts. So this is due to the theorem of Castles and Murphy. What actually happens in the Legendre setting? So I'm going to rotate the picture. So here the handles were side to side, left to right. Now the handles are going to be one on top, one's kind of on bottom, the attaching sphere. So these are portions of the attaching spheres, like maybe there's some like other stuff down here, some other stuff down there. And so this is maybe lambda 1, lambda 2. This is a portion of lambda 1, a portion of lambda 2. And here I slid lambda 1 over lambda 2. And in the Legendrian setting, this is just a piece of the front projection. This is the picture I'm going to get. So lambda 2 stayed the same. So lambda 2 staying the same. The lambda 1 became a connected sum of lambda 1 and lambda 2. So the new picture for the front is going to look like this. I'm going to call this H lambda 2, lambda 1. So in this case, this was my lambda 2. This was my H of 2, lambda 1. So I'm saying, like this region over here, I'm kind of rotating it to picture it as this region. And when I do the handle slide, this one goes over this one, and so it becomes this cusp connected sum. So this is like just a topological connected sum, but explicitly in the Legendrian setting, it has these two colors. And this will be important in a few minutes. Okay, so the point is that you have these Weinstein handle body moves, and those moves are what we mean up here when we talk about pi 0.
They mentioned 3, this is guided, being guided, right?
Oh, this presentation? Maybe, yeah. That sounds right to me. Okay, so let me just add a few remarks to this theorem of Chilibuk and Lily Ashworth, which is that what are the ingredients here? So we have to prove that if two, say, flexible Weinstein structures are formally symplectomorphic, then they are homotopy to these Weinstein homotopy moves. Well, what are these moves? These moves are moving the attaching spheres, canceling or creating handles, or exchanging the order. Well, canceling or creating handles is basically a local operation. And this exchanging the order of the handles is something you can also just check, and you can do it precisely when you can do it in the smooth case. In the smooth case, you can also do it only when the attaching and the belt spheres are disjoint. That's precisely when you can do it in the symplectic case. But I guess the same thing holds for this one as well. So both of these two, you can do in the symplectic case precisely when you can do them in the smooth case. So it's only this one that differs from the smooth case, because now you have to move the attaching spheres through isotropics, versus in the smooth case, you just have to move them through embedded spheres. There's no notion of isotropics. So I would say the proof is the proof idea is to use the H principle for the attaching spheres, so for the subcritical isotropics and the loose Lazarev, which is what we talked about last time, combined with kind of doing these other two moves and analyzing their local models. So I would say maybe, I'm not sure the best way to say it, maybe some local analysis for the other two moves, the moves with handle creation and cancellation and exchange. But you really do need to use these H principles, because otherwise you're not going to be able to approximate an isotopy through smooth manifolds by an isotopy through isotropics. And we also said that the full H principle fails if you just consider all Weinstein domains. Okay, very good. So any questions about that? Okay, so I think I started 5 minutes late. Okay, so in the last 10 minutes, I'm gonna give an application of this. All right. So now I'm going to talk about the simplified Weinstein presentations. Suppose you're given, for example, some Weinstein structure might have a lot of handles. The question I'm going to be interested in is, what is the fewest number of handles for a Weinstein manifold? Kind of possibly after applying these Weinstein homotopy moves. you might have a lot of handles, but maybe you can cancel some handles. Maybe you first need to create some handles, do some handle slides, and then cancel. How can you minimize the number of handles? So I should say that if X is flexible, then let me use some notation. Min Weinstein handle. So that's going to be the minimum number of Weinstein handles for X after applying some Weinstein homotopies. Remember, this doesn't change the symplectomorphism type. So this is actually a symplectic invariant, if you want. This is actually going to be min smooth handles for X. And this is either following or an ingredient for this H principle I stated over here. So basically, if X is flexible, you can do any smooth handle moves can be realized as Weinstein handle moves. Now, well, what is this thing? Well, this thing is actually pretty computable in high dimensions. States the relevant results. Smooth one. Well, I guess. So there's an obvious lower bound for all of these things. Even the smooth one is at least the number of generators for homology. Because one model for homology is this Morse homology, which is generated by the critical points, which correspond to the handles in the body composition. So there's this lower bound, but Smale proved that if n is at least 6, pi 1 of x, or m, I'm going to use m to denote a smooth manifold, is 0, then this min smooth handle of m is just a smooth manifold, is actually equal to the minimum number of generators for the singular homology of M. So this is the type of H principle, actually, right? This is broadly construed. This says this obvious necessary condition is actually sufficient. And what are the tools here? Well, the tools are to use Whitney, to use the Whitney trick to enable smooth isotopies and smooth embeddings. And the Whitney trick uses high dimensionality, so that's where this comes in. And the Whitney trick is also about disks and arcs, so that's where this pi 1 condition comes in. Okay, so this is a type of H principle, but it's in the smooth setting. So now you might ask, well, what happens in the symplectic setting? So, and whether or not this equality holds for things that are not flexible, and actually this inequality, or this equality is an inequality in general. So this is the result Settle Smith from 2006 says that there is a Weinstein domain sigma. I think n is fairly high dimensional. I think it's probably like at least 8-dimensional. I don't quite remember. That is diffeomorphic to a ball, and so it's actually formally symplectic to the standard ball. So it's formally but it's not symplectomorphic to the standard ball. And in particular, it's not Weinstein homotopic to the standard ball. And again, they need to use some non-classical invariants, and they use some flavor of J homomorphic curves. So what does that imply? Well, this actually gives you a bound on the number of handles that you need. So, because if this thing were subcritical, then it would satisfy an H principle, and because it's formally the same as a ball, it would actually be symplectomorphic to a ball. So sigma is not subcritical, so it must have a Weinstein handle of index n. So must have index n handle. And so sigma has at least three, must have at least three Weinstein handles. You must have a index n, and because sigma is a ball, you must have an index n-1 to cancel the index n, and there's always an index 0. So this is to say that min Weinstein handle is not equal to min smooth handle for this exotic ball, because for the ball, the min smooth handle is just an index 0 critical point, and so there's only one. Okay, and in the last few minutes, let me state the result of mine, which is that having at least one, having exactly one index n handle always suffices actually. So here you needed, I guess in total you needed 2 more handles, and this necessary condition is actually sufficient. So if n is at least 3, and x is Weinstein, then min Weinstein of x is going to be so it's either going to be the max of min smooth. So okay, so it's going to be the max. It's either the minimum number of smooth handles, but this might not have any index. Okay, sorry, let me just write it like this. Maybe there's slightly stronger results, but this is, I guess, fine for the statement, which is that having 2 extra handles is enough to get whatever Weinstein structure you want to Y, but 2, well, really you need only 1 index n handle, and then you need a canceling n-1 handle. So in fact, x can be Weinstein homotope to x flex plus 2 handles, and these are smoothly canceling. But they're not symplectically trivial. And this, on the other hand, this is flexible, so it's smoothly trivial. Sorry, it's symplectically trivial, but it's not smoothly trivial. So the picture is something like this. You apply some moves to x, and inside of x, you see its flexibilization, which is what you get by adding zigzags to the handles, and then you have just 2 handles which are smoothly canceling. You've kind of decomposed x into the symplectically interesting portion, sorry, the smoothly interesting portion, but the non-symplectically interesting portion, and a part over here, which is symplectically interesting, but not smoothly interesting, because these are smoothly canceling. So let me just, last minute.
When we say not smoothly trivial, you mean not necessarily diffeomorphic to X.
Which one?
X flex.
X flex is formally the same thing as X.
Is it diffeomorphic to X or not?
Yeah, it's also formally symplectomorphic.
So then what do you mean by not smoothly trivial?
No, this part, okay.
X flex.
I'm just saying all the smooth information is here.
Yeah.
And all the symplectic information is here.
Okay, so it's just X.
It's just that.
Okay, fine.
And the main picture is to think about these handle slides. So recall the picture we had before was this, but we can actually modify this a little bit. So these two are actually isotopic to each other. This is what's called the Reiter-Meister move. And then we do the handle slide. So these are actually equivalent pictures. This is a Reiter-Meister move. And then we do the handle slide. Like this. And now we actually do see a zigzag here. We see a loose chart. Now, the issue is this Legendre is actually going through this loose chart, but at this point you can exchange the order of the handles and attach this one first and attach this one second. So let me just give a very simple example. So this is a Weinstein structure with two index n handles. So it's going to be a cotangent bundle. It's not going to be exactly a proof of this, but it's going to be very close. So this is going to be the boundary connect sum of two cotangent bundles. And okay, in this case, we don't even have to do the Reiter-Meister move. We can just handle slide this one over this one. In that case, we get a picture like this. And this is loose. Now, how do we interpret this picture? Well, these handles can be attached in either order. Like you can attach this one first or this one first. Now, if we attach this one first and this one's not loose, but we can attach. So we can attach this one first. This is some flexible cotangent bundle. And then we attach this other handle, and this is some other handle like this. So the summary is that here we had two handles, and they were both not loose. At the end of the day, we have a handle that is loose, and then some other handle. And then if you have like more Legendrians, you would just again handle slide them over a single one. Again, you would see a loose chart, and you would get maybe two copies of the flexible cotangent bundle. You pick one, and you handle slide everything over that one, and you can make it so that all the stuff that you've handle slid over become flexible. That's how you get this, and then you exchange the order of the handles, and that's how you get this one up top. Okay, so let me stop there. Yeah.
Questions for Oleg?
What is known about the minimal number of smooth handles when pi1 is not 0?
Oh, yeah, I don't know. I mean, that's maybe related to pseudo isotope.
Right, so something maybe related to the French Whitehead group, but I don't know if there's any measure of complexity. Do you know something? Like, so Oleg put a theorem of Smale, right, that if pi1 was trivial, then the minimum number of handles was the number of generators of homology.
Yeah.
And so I'm asking, is there anything you know when pi1 is not 0?
Depends on the unitary stable rank of the. So yes, but it's an algebraic data.
And there's a theorem that says it's the rank of homology plus this unitary stable rank.
It's true, I don't know what.
But are there examples when the minimum number of smooth handles is strictly bigger than number of generators. Okay,
Think about like an H chord is a non-trivial torch.
right, okay, okay. But what about those? Okay. Okay, multisphere.
So it's strictly greater than the
Right.
minimum number of generators in a presentation of pi one plus the rank of homology from 2 upwards. Is that,
Yes, I guess also, yeah, that's also.
because that's kind of a
That's gets with torsion,
that's definitely a lower bound, right? So the question is it just bigger than that?
because those are torsion thing.
Right.
But you know, like it's somehow like the size of matrices representing all the elements and stuff, like that.
I, towards the beginning, when you said, I think maybe philosophically, we should think of Weinstein manifolds as being cotangent bundles of singular isotropics. Was that only if you had isotropic cores of dimension n? Like what if you just have ones of less than n, do you still think of it that way?
I mean, I do,
I guess
okay,
I'm
you get
just asking if that like correct for me to think of it later or not.
Well, this is what I think Kai was pointing out, like a one, like just a ball. The standard ball is not a cotangent bundle of something, but you could also say cotangent bundles of manifolds with boundary. And if you do that, then its cotangent bundle will be a ball, but there'll be a bit more data, which is the data of how the boundary of the disk intersects. Like, what I'm trying to say is that the cotangent bundle of a disk, you should think of this as the standard ball, but you should also kind of remember this extra, I mean, one can remember this extra boundary data. And this is a Legendre in here. So cotangent bundles of things with boundary are these things that are called Weinstein sectors, which are Weinstein domains plus some Legendre in the boundary. And so this is to say that I think you were asking about subcritical handles.
Yeah.
And you could think of a subcritical handle, so you can maybe view it as a cotangent bundle of a manifold with boundary.
Oh.
Yeah. So just like this, right? This is not actually a cotangent bundle of something. But if you kind of want to think about this, it's a cotangent bundle of a disk, which is a manifold with boundary. Yeah.
You thought of maybe, in one parameter family, stuff like pseudo-isotopy type problems. So like you have a one parameter family of Weinstein manifolds, and maybe at either end they look like this, and then maybe you could also concentrate the one parameter family to have something that's happened flexibly, where maybe you have all the smooth pseudo-isotopy stuff, and then you localize to those two handles whatever extra symplectic phenomenon is going on, and maybe you can say you have anything beyond.
You're asking about like a parametric version of
Yeah.
I haven't thought about it, but it seems reasonable. Yeah, I mean split pseudo-isotopies, we were talking about this. There's like we don't know that much, and I think that's
Right, but maybe with
Yeah.
this you could just at least separate it into two different. Like if you had a one parametric version of this, then at least you could then try to address that problem with two pieces.
Right. Let me maybe make one tangential remark, which is that, so the standard cotangent bundle of a sphere, it has a presentation where you have a single n handle attached along the Legendre unknot. But there's actually another presentation for it, where it's again a ball with a single n handle, and that n handle is attached along Legendre, which is not the unknot. So it has some different DGA. And they're homotopic. So there's some moves you do, you introduce some canceling pair, you do some handle slides, you go from this one to this one, but you can't simplify it, even though like smoothly you can.
Right.
And this is not quite a loop, right? Because you end up with two different Legendre knots, but it's kind of in that direction.
When you have zigzag attaching spheres, make them loose. So you might not be symplectomorphic, but other boundaries still.
No. Okay, this is actually what I proved in my thesis, that the contact boundaries can remember the topology of, well, the answer is no, almost always. I mean, if the original thing were flexible, it's still flexible. But let me just say that these flexible Weinstein domains are good for constructing exotic contact structures. So, which is say that if the homology of X is not isomorphic, let's consider two flexible Weinstein domains, but they could have smoothly the same boundary. They have different homologies, so they're not diffeomorphic, but maybe their boundaries are diffeomorphic. Then the claim is that the boundary of this one is not contactomorphic, the boundary of this other one. So, but the boundaries could be diffeomorphic. The claim is the fillings have different homology. And using this, you can actually construct infinitely many contact structures on a fixed smooth manifold. So actually you can produce some examples of rigidity using some things that are maybe more on the flexible side.
So if the fillings are diffeomorphic, then you cannot.
Well, if the fillings are diffeomorphic and flexible, then they're basically symplectomorphic.
No, but like for example, for this T star SN and T star FN flex, you don't get.
This result doesn't apply to that setting because one of them is not flexible. But
Sure, but still, as one chain domain, you have like the boundary is contact manifold.
the boundaries are not the same. So the boundary of a flexible cotangent bundle and the boundary of a cotangent bundle are not contactomorphic. This is a related result, which you can use to construct infinitely many contact structures, but it doesn't answer your question right there.
Okay, and so for what you just said, so boundary of something not flexible and boundary something flexible will not be contactomorphic. This is what you're saying.
I said in that particular example, the contact structures are not the same. I don't know in general.
So for T star S2, for example, you get something.
Well, T star S2, if you flexibilize it, it's going to be in a different formal class. This is this issue about adding zigzags, changing the formal class. In high dimensions, you can add zigzags without changing the formal class. Everything is still the same. They're not symplectomorphic. Furthermore, the contact boundaries are not contactomorphic. It doesn't follow from this, but there's some related results.
Okay. Well, let's thank Oleg again for that.